Okay, so let's discuss about the electric potential energy. When a charged particle moves in an electric field, the field exerts a force that can do work on a particle, and the work can be expressed in terms of the electric potential energy. Consider, for example, here, you have a charged particle in a parallel plate, so in between two parallel plates. So above, you have a positively charged plate, and then below, you have a negatively charged plate. These plates produces a uniform electric field that points from your positive plate towards your negative plate downwards. Now, if you have some electric charge here, some test charge uh, in between your parallel plates, this charge experiences a force which is equal to Q naught E, which is the force exerted by the electric field on this test charge here. And the field exerts a force that can do work on the particle. And this work can be expressed in terms of the electric potential energy. If you remember, your work is equal to a work done from A to B. If, let's say, your particle moves from point A to point B here, this is equal to your force times your displacement. And since your force, which is exerted by the electric field, is equal to Q naught E, your work from A to B is equal to Q naught ED. Okay. Now, the electric potential energy depends only on the position of the charged particle in the electric field. That is, however you move from in your electric field, whether it is directly from A to B downwards, or you move this way, or either you move in this way, the electric potential energy depends only on the position. So it just depends on A and B. The electric field due to a static charge distribution generates a conservative force, similar to your gravitational potential energy. So you have your work from A to B is equal to your negative delta U, where your U is your electric potential energy, which is equal to Q naught E, E times your distance Y. Okay, so this is familiar because this is how your gravitational potential energy looks like. If you have a positive charge moving in a uniform field, like say for example here, you have your positive charge, and we still have the same parallel plates, positive plate above and a negative plate below. You still have this uniform electric field from your positive towards your negative plate. Now, if you have a positive test charge that moves in the direction of the electric field, that is, it moves downwards here. Now you know that your test charge, your positive test charge is attracted to your negative plate since they have unlike charges. So your test charge experiences a force that is downwards here. And if your test charge again moves in the direction of E, meaning it has a displacement that is downwards, the field does a positive work on the charge. This is just similar to what we have discussed in work in your mechanics, that if your force and then your displacement is in the same direction, you have a positive work. So here, the field does a positive work on the charge. So because it is just your work is equal to your F times your displacement, and this is equal to FD cosine theta. So if cosine theta is 0, meaning your force and then your displacement is parallel, then you have a positive work done. So here you have a positive work done by the field on the charge, and your electric potential energy decreases. If you have a positive charge that moves opposite E, like say for example here, your displacement is upward, so but still the force experienced by your charge is downwards because it is attracted to your negative charge. So as you can see here, the force and then your displacement is in opposite direction. So for this case here, the electric field does a negative work on the charge, and your electric potential energy decreases. So the work done from A to B for a test charge that moves from a height YA to YB is equal to the negative of delta U, where this is equal to the negative of UB minus UA, or since your U is equal to Q naught EY, so you have Q naught E times YA minus your YB. If instead you have a negative charge, and here your negative charge here, this is attracted to your positive plate. So the force exerted by the field is directed upwards. Okay. Now, if the negative charge moves in the direction of E, that is, if it moves downwards, your field does a negative work on the charge. Because as you can see here, the force and then your displacement are in opposite direction. That is, here, your force is upwards, but your displacement is downwards. So your FV cosine theta, you have theta which is equal to 180 degrees. So you have here, which is your cosine theta is a -1. So for this case here, the field does a negative work on the charge, and your U, your electric potential energy, increases. If instead the negative charge moves in opposite direction with your electric field, so the electric field here is downwards, but your negative charge moves upward, the field does a positive work on the charge. Because as you can see here, your force is upward and then your displacement is upward. For this case here, the potential energy U decreases. And independently of whether the test charge is positive or negative, U increases if Q naught moves in direction opposite to the electric force, and U decreases if Q moves in the same direction as your force, which is equal to your Q naught E. Again, U increases, your electric potential energy increases if Q naught moves in direction opposite to the electric force, and U decreases if Q naught moves in the same direction as your electric force, which is equal to Q naught E. Now, that was the case when you have a charge that moves in a uniform electric field, like say, for example, a uniform electric field created by two parallel plates. But what happens if you have 2-point charges, and one of the point charges will be your source of your electric field? So this is the electric potential energy of 2-point charges. Consider, for example, you have a charge Q, and then you have another charge, a test charge Q naught. And this test charge Q naught moves from A to B along a rigid line from Q that moves from here, from point A, until point B. And remember that this charge Q here creates a field around its surrounding, which is all radially outwards. And you have some line here, a radial line, which also has an electric field line. And we are looking at this test charge here that moves in one of the electric field line of this charge Q here. Now, if these are both positive, like say for example, if the test charge here is positive, a test charge Q naught will move directly away from a charge like Q, since your Q is also positive, and your Q naught will be repelled by your charge Q here. And if you want to find for the work done on this test charge Q naught here as it moves from A to B, the work done from A to B is just equal to the integral of this function here. You have your FR dr, and looking at your dr as an infinitesimal movement or infinitesimal displacement. So integrate this one from RA to RB. And remember that your force or your point charges is equal to 1 over 4 pi epsilon naught Q times Q naught over R squared. So this is your force for your point charges from your Coulomb's law. And dot with your dr, and then integrate this one, evaluate your integral. So we are just evaluating your dr over R squared, which is equal to your 1 over R, and then evaluate from RA to RB. Your work from A to B is equal to Q times Q naught over 4 pi epsilon naught 1 over RA minus your 1 over RB. So this one here, this is the electric potential for electric potential energy for 2-point charges. Now, these are the graphs of the potential energy. Again, the potential energy when charge Q naught is at the distance r from Q is equal to this U here, which is equal to Q times Q naught over 4 pi epsilon naught R. Okay, and again, the work done from A to B is equal to Q times Q naught over 4 pi epsilon naught times 1 over RA minus 1 over RB, which is equal to the negative of delta U, where again, your delta U is equal to this quantity here. If the two charges have the same sign, if Q and Q naught are both positive, or they may be both negative, the potential energy for these 2-point charges is a positive. That is, it's greater than zero. You have a positive times a positive, it's a positive, and then negative times negative is positive. So for this case here, if they have the same sign, the potential energy is positive. And as R approaches to zero, that is this distance between the 2-point charges becomes smaller and smaller, the potential energy approaches infinity. So if this is R here, if this R here approaches to zero, your potential energy approaches to infinity, positive infinity. And as R approaches to infinity, that is, if the distance between these two here becomes very, very far, that means that these two charges becomes very, very far apart, then the potential approaches to zero, as you can see here. If this R here becomes bigger, this potential energy approaches to zero. That is, they do not anymore experience the potential energy that is created from the from both charges. If Q and Q naught have opposite signs, may it be that your Q is positive and then your Q naught is negative, or your Q is negative and then your Q naught is positive. For this case here, the potential energy is a negative. So you have a positive times a negative, it's negative. And as R approaches to zero, as these two becomes closer together, the potential energy approaches negative infinity. And as R approaches negative infinity, that is, as they go farther and farther apart, your U approaches to zero, as you can see here. If R becomes greater, this curve here approaches to zero. And as you have seen in the previous slide, your electric potential energy is a shared property of two charges. It's a consequence of the interaction between them. If the distance between two charges is changed from RA to RB, delta U is same with whether Q is fixed and Q naught is moved or vice versa. That is, the electric potential energy is the same whether you have your Q fixed and then you move Q naught, or you have Q naught fixed and then you move your Q. If, say for example, you have several point charges, that is, you have 3 or more charges, the potential energy associated with Q naught at A, okay, if you have some Q naught here at location A, the potential energy is the algebraic sum of U associated with each pair charges. In this case here, you have Q1, Q2, and Q3. Then the potential energy associated with Q naught here is just the potential energy of Q1 and Q naught plus Q2 and Q naught plus Q3 and Q naught, which is mathematically, you have your U is equal to Q naught over 4 pi epsilon naught times Q1 over R1 plus Q2 over R2 plus Q3 over R3 plus so on and so forth. Or that is your Q naught over 4 pi epsilon naught times the sum of Qi over Ri, where your I is the number of your charges associated with your Q naught. Okay, let's have an example. A point charge Q1 of charge plus 2.40 microcoulombs is held stationary at the origin. So you have your point charge here Q1 stationary at the origin, and a second point charge Q2 negative 4.30 microcoulombs moves from 0.150 meters x to 0y. So initially it's from here, the x-axis, 0.150 meters from Q1. And then it moves from A to B, where B is x 0.250 meters, y 0.250 meters. So it moves from here to here. So the question is, how much work is done by the electric force in Q2? So you're asked for the electric force, the work done by the electric force in Q2 as it moves from point A to point B. So, but before that, let us find for distances R. So RA, since this one here, this is just your x axis. So your RA is just 0.150 meters. So your Q2 is just 0.150 meters from Q1. And then for RB, you have this one here. So the location of your point B is at 0.250 meters x and 0.250 meters y. So you create some triangles here, and then to find for this distance, you just use your Pythagorean theorem, which is just your RB is equal to the square root of 0.250 meters squared plus 0.250 meters squared. So this is your x squared plus y squared. You get the square root, and then you get your RB. Your RB is equal to 0.3536 meters. And let us use this values here, later in finding for the work done by the electric force in Q2. The electric force is this force here from your Q1. So let's solve the problem. So we're asked to find for the work done as your Q2 moves from A to B. That is your UA minus your UB. So if you have your UA and then your UB here, let's find first your UA. Your UA is just your 1 over 4 pi epsilon naught Q1 times Q2 over your RA. Okay, this is just from your formula for 2-point charges. Your 1 over 4 pi epsilon naught is this value here. And then for your charges, let us use the standard units. So you have 2.40 times 10 to the negative 6 coulombs, and then negative 4.30 times 10 to the negative 6 coulombs. So again, we are using here your standard units, which is in coulombs, divided by your 0.150 meters. So this is now your UA. And then solving for this one, you get an answer of around negative 0.6184 joules. So you now have your UA. Now let's find for your UB. Your UB is just 1 over 4 pi epsilon naught Q1 Q2 over RB. Okay. This time here you have your RB. So 1 over 4 pi epsilon naught is again just this constant here. Q1, this is your Q1, and then your Q2 divided by 0.3536 meters, this distance here from Q1 to point P. Your UB is equal to negative 0.2623 joules. Now we now have your UA and then your UB, so we can now solve for the work done from A to B, which is just your UA minus your UB, or you have your negative 6.6184 joules minus the negative 0.2623 joules. The work from A to B is equal to negative 0.3536 joules. Okay, so now let's talk about the electric potential. Your electric potential is different from your electric potential energy. Your electric potential, or simply your potential, is your potential energy divided by your unit charge, or your potential energy per unit charge. And your electric potential, we use the symbol V. Your V is equal to your U over your Q naught, where your U is your electric potential energy. So it's your potential energy per unit charge. And here your potential is a scalar quantity, and it has units of volt, where 1 volt is equal to 1 joule per coulomb, or 1 newton meter per coulomb. And since the electric potential, or your potential, is potential energy per unit charge, let's find this one here. So the work done from A to B is just the negative of delta U. You divide it by your unit charge Q naught, find for the potential. So you have, this is equal to negative UB over Q naught minus UA over Q naught. And interchanging some of the values, you have your BA minus your BB. This is equal to BAB. Your VAB is the work done by the electric force when a unit charge moves from A to B. And this is similar to your voltage, okay? Which in the case for the battery, the potential of a battery can be measured between points A and B, where your A is the positive and then your B is your negative terminal. So what you're actually measuring here is the potential of your battery, which is equal to VAB, which is VA minus your BB. These are some of the formulas you can use to calculate your electric potentials. For a single point charge, the electric potential is just your U over Q naught, which is 1 over 4 pi epsilon naught Q over R. If you have a collection of point charges, just sum the potentials of the individual charges, that is your electric potential is equal to 1 over 4 pi epsilon naught times the sum of Qi over Ri, where I is the number of your point charges. And for continuous distribution of charges, we have 1 over 4 pi epsilon naught and then the integral of dq over r. Then just evaluate this integral to find for the electric potential of your continuous distribution of charge. And you can also find the electric potential from an electric field. Given the electric field, remember that your voltage VAB is equal to VA minus VB, and this is equal to Q, or this is equal to work from A to B divided by Q naught. Your work is your force times your displacement, evaluated from A to B, divided this one by Q naught. But remember that your force is given by your Q naught E. So this term here becomes Q naught E, that EL over Q naught. And dividing this one, your Q naught divided by your Q naught, so you're just left with the integral of E dot dl, where you have your E cosine P dot dl. So you can use this one to find for the electric potential given the electric field E. This is again finding the electric potential from the electric field. If, say, for example, you have a positive charge, then a negative charge. If you move in the direction of the electric field, the electric potential decreases, but if you move opposite the field, the potential increases. As you can see here, for a positive charge, wherein the electric field lines are radially outward, your potential B increases as you move inward. Your negative charge increases. The value of your B increases as you move inwards, and your B decreases as you move outward. For a negative charge, your B decreases as you move inward, because you move in the direction of the electric field, and your B increases as you move outward, because here you move opposite the direction of your field. So in here, your B increases as you move outward. So again, for your positive charge, as you move inward, the value of your electric field, your electric potential increases and decreases as you move outward. For a negative charge, as you move inwards, B decreases, and as you move outward, B increases. Let's review some of the units. So for your electric charge, it's given by your column C. For your electric potential, you have your joules, and then for your electric potential energy is in joules, and then your electric potential you have in volts, and then your electric field is in newtons per coulomb or in volts per meter. For a particle that moves to a point from where the potential is VB to a point where potential is BA, your UA minus your UV, your work done, is equal to your Q times VA minus VB, or your Q times your voltage, Q B AB. If Q equals the magnitude of your electron charge, where the charge is equal to 1.602 times 10 to the negative 19 coulombs, your UA minus your UV is just your charge, electron charge, E times 1 volt. So you have 1.602 times 10 to the negative 19 joules. So since we're talking here about 1 electron charge, so your 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. 1 electron volt is a quantity of energy. So aside from your electric potential energy with a unit of joules, we can also use your electron volt, where your 1 electron volt is equal to 1.602 times 10 to the negative 19 coulombs, which is easier when times we're talking about the charge of your electron charge. So we're just going to remember 1 EV, wherein 1 EV is equal to 1.602 times 10 to the negative 19 joules. These are your units: coulombs for electric charge, joules for electric potential energy, volts for electric potential, and Newton per coulomb or volts per meter for your electric field. Now let's have an example. 2 points Q1, or 2-point charges Q1 with a value of positive 2.40 nanocoulombs, and Q2 of negative 6.50 nanocoulombs are 0.100 meters apart. So you have these two charges here, Q1, Q2 separated a distance of 0.100 meters. Point A is midway between them, so you have point A here, and point B is 0.080 meters from Q1 and 0.060 meters from Q2. Take the electric potential to be 0 at infinity. Okay, so as your R approaches to infinity, your electric potential approaches to 0, and these are the problems. Find A, the potential at point A, the potential at point B, and the work done by the electric field on a charge of 2.50 nanocoulombs that travels from point B to point A. So you're asked of the following: the electric potential, or the potential at point A here, the potential at point B, and then the work done as a charge of 2.50 nanocoulombs moves from point B to point A. So this is problem for this figure here. So now let's solve the problem. So this is again your figure. So you have your two charges, Q1 and Q2. And then you have here your point A, where we find the potential at point A, and then point B. Okay, and then you have the measurements here of the separation distance R. Remember again that your voltage, or your potential, is equal to 1/4 pi epsilon naught times the sum of your Qi over Ri, where your I is the number of your charges. So let's find for the potential at point A here. We just use this formula here. So you have your VA is 1/4 pi epsilon naught times Q1 over RA1. Okay, your Q1 here, and then the distance of Q1 from A. So your RA1 plus Q2 over RA2. So Q2 here, and then this distance here from measured from your Q2 to your point A. This is the potential at point A, and then inputting the values. So your VA is equal to your 1/4 pi epsilon naught, which has this value here, 8.988 times 10 to the 9 Newton, that meter squared per coulomb squared. And then use the standard units. So your Q1 is 2.40 times 10 to the negative 9 coulombs divided by 0.050 meters, plus negative 6.50 times 10 to the negative 9 coulombs divided by 0.050 meters. So again, here we are using your standard units. And using your calculator, we can calculate the potential at point A, which is equal to negative 737 volts. So that is the potential at point A. Next, we find the potential at point B here. We still use the same formula. We still have the same point charges, but in this case, we have a change in the distance from point B. So you have your RB1 and then your RB2. So your RB1 is the distance from Q1 to B, and then your RB2 is the distance from Q2 to B. So the same formula. And your VB, you have 1/4 pi epsilon naught, which has this value, times your Q1 divided by 0.080 meters plus your Q2, negative 6.50 times 10 to the negative 9 coulombs divided by 0.060 meters. And using your calculators, we get an answer of negative 704 volts. So this is the potential at point B. Next, let's find for the work done by the electric field and a charge of 2.50 nanocoulombs that travels from point B to point A. So you have this time a charge of 2.50 nanocoulombs that travels from point B to point A. Okay, so your work is just your Q VB minus your VA. If you remember, in case if ever you forget, your voltage, or sorry, your potential is equal to, your potential B is equal to your U over your Q naught. Okay, and your U then is just equal to your Q naught times your V. But your work is equal to the negative of delta U. So you have then this change of this quantity here. That is why we have this one here. So you have the work from B to A is equal to your Q prime, which is equal to 2.50 nanocoulombs times BB minus VA. So you have 2.50 times 10 to the negative 9 coulombs. Again, we use the standard units. Times your BB minus your BA, which we have solved earlier. And that is equal to negative 704 volts minus negative 737 volts. And evaluating this one, you have the work from B to A is equal to plus 8.2 times 10 to the negative 8 joules. So you have here the work done as a charge of 2.50 nanocoulombs travels from point B to point A. We have this what we call your equipotential surfaces. Now, an equipotential surface is a surface on which the electric potential is the same at every point. Again, an equipotential surface is a surface on which the electric potential is the same at every point. And the field lines and equipotential surface are always mutually perpendicular. So consider this one here for a positive test charge. Your electric field lines move out radially outward. And since your equipotential surface and your field lines are mutually perpendicular, if you have more electric field lines here, you'll see that if you draw perpendicular lines with your with your field lines, you'll see later that you're actually forming circles around your charge. And one circle here, if you're going to measure the potential around this one circle here, anywhere around this point, you get potential of equal value. So you call this circle here as an equipotential surface. And take note that this is three-dimensional. We're just looking at the cross section. So you're actually having here a sphere surrounding your charge, and the sphere it has or is an equipotential surface. For example, this surface here has a potential of plus 30 volts. And as we've said earlier, as you move inward your charge, your potential increases. So from 30, as you move inwards, you have 50 volts. As you move inner, you have 70 volts. This is the electric field lines and equipotential surface for your dipoles. Okay, so you still have the circles. Okay, and for your negative charge, as you move um, deeper, okay, your equipotential, you have here your potential, which has a negative value. So the outside surface, you have negative 30 volts, and then as you move deeper, it becomes more negative. So you have inner potentials. The inner surface has a voltage of, let's see, you have a negative 70 volts. Now for your dipoles, it's interesting that in the middle, between the two dipoles, your potential is equal to 0. This is, on the other hand, the equipotential surface um, for your two positive charges, two equal positive charges. So now, when talking about your conductors, when all charges are at rest, the surface of a conductor is always an equipotential surface. And the electric field just outside the conductor is always perpendicular to that surface. The entire solid volume of a conductor is at the same what you call this, is at the same potential. So if this one here, this is your conductor here, and you're going to measure the potential anywhere around here. So you are going to measure the same potential in your surface. Now, previously we have this theorem that in an electrostatic situation, if a conductor contains a cavity and if no charge is present inside the cavity, that is this one here, if there is no charge here, then there can be no net charge anywhere in the surface of the cavity. That is, there should be no charges here. And the charges should just reside on the surface of your conductor. To prove this point, remember that every point on the conductor is at the same potential. So we've said that the surface of your conductor is an equipotential surface. Now, your BB minus your BA, if let's say we take some 2 points, BB and BA, Now your BV minus your BH is equal to the negative of the integral of E that ds is for this case here. Okay. Now now we have said that for your conductor, the surface is an equipotential surface. So that means your BB minus your BA, wherever you point your B and then your A in the surface of your conductor, your BB minus your BA is always equal to 0. That is, this integral here must be 0 for all paths between points A and B. And the only way that this can be true, for this one to be 0, is for all paths is if A is 0 everywhere in the cavity. So there should be no charges here for this equation to be true. Okay? Because if there were charges here, then that means there is electric field here, and you will not be able to get your BD minus your BA, which is equal to 0, because of the presence of electric field here, if ever there is an electric field in your cavity.